Testing, 1, 2, 3. You don't have any sound.
Yes, you do.
Oh, you do? Hello? No. You see sound there? Okay. There's sound. I now call to order the Society's 2,393rd meeting in the 148th year since its founding in 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Tamás Budavári in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science YouTube channel. We will begin with a few announcements, a reading of the minutes of the 2,392nd meeting and Yuval Grossman's lecture on antimatter, and then turn to this evening's lecture, which will be followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and then adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2017 and Spring 2018 lecture series, the Policy Studies Organization, in cooperation with the American Public University, and a generous sponsor who has asked to remain anonymous. I am pleased to announce that tonight's speaker, Tamás Budavári, has been elected to membership in the Society. Please join me in welcoming him. Recording Secretary James Heelan will now read the minutes of Yuval Grossman's lecture on antimatter at the 2,392nd meeting.
Good evening. On April 20th, 2018, President Larry Milstein called the 2,392nd meeting of the Society to order at 8:11 p.m. in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting and the lecture by Don Norman were approved without correction. President Milstein then introduced the speaker for the evening, Yuval Grossman, professor of physics at Cornell University. His lecture was titled, "The Mystery of Missing Antimatter. Why is the Universe Made of Only Matter?" Grossman said, "When there are open questions in physics, it often means there are multiple possible solutions. As to baryogenesis," he explained, "there is a predominant theory, but there is one experimental result that the theory cannot reproduce." He went on, "Matter is made of particles including baryons, leptons, and neutrinos. Scientists have determined that each of these particles has an antiparticle of the same mass and the opposite charge. But," Grossman asked, if antimatter is a mirror image of matter, where is it?" He offered several potential answers, which scientists have disproven. The remaining theory is that matter and antimatter are not exactly the same thing, and that matter was generated in the Big Bang. Grossman then explained current theories for where various elements were created. In sum, he explained that scientists have determined that matter was created within the first 3 minutes of the Big Bang at a density of 1 proton per 5 cubic feet. Grossman then moved to how matter was created. The laws of conservation tell us that charges cannot be created or destroyed, and that when charged particles decay, they decay into other smaller particles. But scientists have not observed proton decay. To To explain the lack of decay, scientists have invented a new conservation law called the baryon number, which keeps the proton stable. However, the baryon number implies that a proton cannot be created or destroyed without an antiproton, which begs the question, how can we end in a universe made of protons? In 1967, Andrei Sakharov answered the question with three conditions. First, the baryon number is not conserved because there must be a way at high temperature to generate a baryon without an antibaryon. Second, matter and antimatter are not exact mirror images. Otherwise, the same amount of baryons and antibaryons would have been generated at the Big Bang. And third, the process cannot be in equilibrium. Otherwise, the same amount of baryons that are created are also destroyed. According to Grossman, the three Sakharov conditions all fit within the standard model. However, the standard model predicts 1 proton per moon volume rather than 1 proton per 5 cubic feet. Because the standard model cannot explain the data, there must be new particles with new interactions and bigger differences between matter and antimatter than previously thought. These are the new open questions in physics. The grand unified theory, lepton genesis, and supersymmetry are amongst the current competing theories. To check these theories, scientists may use proton decay, beta decays, and specific signals at colliders. Grossman concluded optimistically that we may have consensus on the new theory within his lifetime. President Milstein then invited questions from the audience. A member asked how scientists knew matter was created within 3 minutes of the Big Bang. Grossman answered that what scientists really know is the temperature, which they have translated into minutes to more easily communicate their findings to the public. Another member asked why so many antimatter experiments compare only antihydrogen to hydrogen. Grossman said, ideally, scientists would use antideuterium, but they do not yet know how to create it. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:31 p.m., President Milstein adjourned the 2,392nd meeting of the society to the social hour. Temperature, 13°C. Weather, clear. Attendance, 100. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any corrections or comments on the minutes? If you could turn down the volume a little bit. It's the one on the right. Just a little. We'll see. Okay. If not, I will entertain a motion from a member to accept the minutes as read. Bob, second. All members in favor? All members opposed? There being no opposition, the minutes are accepted unanimously as read and will be posted to the website in due course. We now turn to tonight's lecture on big data, and it is my pleasure to briefly introduce tonight's speaker, Tamás Budavári. Thomas is a professor in the Department of Applied Mathematics and Statistics at the Whiting School of Engineering at the Johns Hopkins University. He focuses on the mathematical and computational challenges of big data. He's the builder of the Sloan Digital Sky Survey and its data solution, Sky Server. He also created the Hubble Space Catalog, a searchable database of all Hubble Space Telescope observations. These both involve truly large data sets. Among other awards, Tamás is the recipient of Statistics and Applied Mathematical Sciences Institute's Gordon and Betty Moore Fellowship. He earned an MS in Physics and a PhD in Astrophysics from Eötvös-Loránd University in Budapest. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Tamás to the podium. Tamás. I think we're not at the beginning here.
Okay.
This works about right.
Now you're looking at all my slides in reverse order.
This is the very fast version for speed readers.
Yeah, exactly. Okay. Check, check. Yeah, thank you very much.
That's backwards. To the right is forward.
Okay.
Let's see if it's working. It is. And there's a pointer. The top is the pointer.
Perfect.
And the bottom is when you don't want anybody to see your slides.
Okay. Two microphones. Loud enough, but for everybody else that's not in the room, I guess will be tricky. I understand. Okay, let me know when I'm good to go. Okay, check, check. I think we are good. So, thank you very, very much for the invitation, the very, very kind introduction. I think it's safe to say that this is by and large the most beautiful I've ever given a talk in, but most importantly, I want to thank you for the warm welcome that I received when I came here. This is really just a fantastic experience for me so far, and I'm hoping that I can share with you essentially a really interesting story that we have been developing over several years now. President Milstein told me that I should take my time and tell you my whole story. I promise I won't do that. I won't tell you my whole story, but I will try to tell you about all the relevant bits and pieces that go into this project. I will not tell you about maybe hardware development and GPU programming, and I will not tell you about some other aspects of spatial databases and indexing, but I will tell you everything that goes into this project, and hopefully it will be something that keeps you interested, and I'm more than welcome, more than happy to entertain questions at the end. Okay, it's data science talk. Okay, so my forte is not in art or history, but I wanted to take the time to set the stage for the problem we are trying to solve. Okay, so if you drive up just down the road to Baltimore and arrive to the Inner Harbor from the south, and you find yourself, where the Science Center is and the Visionary Art Museum. You can go up to the Federal Hill and look down to Baltimore. Well, if you did that in 1831, this is what you would see. Okay, Baltimore has just some fascinating geographical potentials. I think I would go even as far as some might say that it's a view that's almost like Sydney's harbor, and in fact, I don't know if you know this, but Darling Harbor in Sydney has been modeled after the Inner Harbor in Baltimore. But I'm jumping too much ahead in time because I wanted to first show you what the other side of the bay looks like. So this is 1830 or maybe 1850. These old postcards that you can find on the web, because the internet is just a wonderful thing, show how Baltimore Street looked like. And this is this vibrant, lively city that you would want to move into, right? Look at that picture. I mean, streetcars on the road. Want to live there? I know I do. All right, so what drives this city and what makes the growth of this city very fast in this era is essentially industry moving in, mills, steel, and very urban things like an umbrella factory. Okay, so Baltimore was the home of the oldest umbrella house in America. And just fascinating history if you go to the Industrial Museum in Baltimore. I recommend the trip. It's definitely worth it. Here is, so we are probably fast forward. This is City Hall, 1860-70, just about the time when PSW is funded, and Johns Hopkins University, coincidentally, at the same time. So just for reference, Los Angeles at this time is about 5,000 people. Okay? Baltimore is already a city of 300,000 people. DC is maybe half of that. So from this, Baltimore is growing very fast. And here is how our campus, which used to be far away from the city, now it's practically in the city. It is in the city technically, but it is a very integral part of the city, very close to. But for those years, I guess travel was a little slower and everything took a little longer. But this is our campus with just a few buildings: the original Homewood House, the original owner's house, and the Gilman Hall and the greenhouse behind it with a garden, and the university lecture rooms and buildings that are currently also still there. So this is the same picture essentially today. Here is the Hopkins House and the circle, which we call the beach. And the Gilman Hall across from the library is there, and the park, and the power plant, which right next to the Applied Maths department, which is where I primarily live, and a whole lot more other buildings, right? So this is good. Everything's changed since then, not just black and white and color, but there's a whole lot more houses and buildings because there is population growth. All right, so I couldn't resist to sneak in a picture that I took from Federal Hill of Baltimore. Okay, this is how I see it or saw it in 2009, and I went up there. And of course, I don't take it by hand. I don't handcraft these pictures anymore because we have big data, and we have cameras that we can use. Every cell phone is a big data generator, if you like. And I took more of these pictures so that you see how that looks. This is Baltimore, right? Baltimore Inner Harbor and the aquarium. But Baltimore is not just lights and the beautiful new buildings, but it's also a fusion of the past and the current and the modern life. In fact, if you walk around with your eyes open, you will see a number of ghost signs or signs that are faded on the walls, and I think they're just absolute gems and treasures to look at. So here's one by the University of Maryland campus. On the side of a house. You may or may not see it if you don't look carefully. This one is from the 1800s advertising pajamas. How appropriate for today, right? So, or nightgowns, or just wares for the evening. And wherever you go, you just see and you feel the past in Baltimore. It's just a great feeling. And here's our city hall, which looks just the same as it looked back then, I think, or almost. Here's another picture. All right, so not everything in Baltimore is new, and not everything in Baltimore is for the better. There is a side of Baltimore that looks like that. And in fact, there are many of these houses. These are boarded up, vacant houses that were abandoned a long time ago. The city knows about them. And they are arguably the source of much of the problem that you hear about that is in Baltimore. Okay, so these are essentially places where crime can take place. These are places where people will not safe going by, and living next to a vacant house is not a great thing for anyone. So the question is, how do you deal with a situation like this? If you had all the money in the world, or just enough, then you could solve the problem like that. It would take a little longer. But what if you have limited amount of money, which is usually the case in resources? What can you do? What can you do? Okay, so this is where we are going. This is what we would like to help with. Here is a curve that was compiled by Phil Garboden, who we will meet later on. It's a population of Baltimore as a function of time. So the growth I explained here is not quantified and shown on this graph. What you can see here is that from the original, say, 300,000 people at the time of the foundation of Hopkins or PSW, you grow really fast all the way till 1950, and there's a number of reasons for this, of course. And then after, there's a decline. Okay, and there's many reasons for this, both the growth and the decline. The growth is probably easier to explain due to industry and all the historical events that happened between 1900 and 1950. But after that, the number of things that happen in Baltimore that make this decline essentially so rapid. And currently, it seems to be leveling off, but there is a lot of changes still in the city. I've known personally and lived in the city for more than 15 years at this point, and it is very interesting to see the change. And just in that period of time, you can see a lot of change. Most of it I see is for the better, but then there's areas that I just showed where things are changing for the worse. And so, how do you deal with the situation in a scientific way and try to use data to make the right decisions? So, in terms of numbers, okay, Baltimore has lost a third of its population since 1950. That's a huge drop. And there are 17,000 boarded up vacant houses in the city. Okay? Some might argue, and in fact, most people who think about these problems think that there is a whole lot more abandoned houses in the city that are not on this list yet because they haven't been recorded, they haven't been categorized, they haven't been captured and put into a database. So there is vacant that we know about, and there is abandoned that we don't know about, or unoccupied that we don't know about. So here is a map of Baltimore, where on the left-hand side you see a very nice, colorful picture of how the market is ranked into categories, the regional choice being the best market, the strongest market where you would prefer to buy a house if you can, whereas distressed markets are places where people don't really look for houses very often. But this detailed analysis is really just showing a very similar trend or a very similar picture of what you see is just when you plot the boarded up houses. So just looking at vacant houses essentially gives you roughly the idea of how Baltimore looks like, what's going on, and a good proxy for many things. So once again, board-ups and vacants are the source of many of these problems, many of the problems in Baltimore. So how do you think about these things? I don't have time to go into the details of my journey to arrive at this project, but I would like to point out that the Institute for Data Engineering, the Institute for Data Intensive Engineering and Science, IDS at Hopkins, is where many of these ideas and projects started at Hopkins. It's no coincidence that the project's website is showing an astronomy image in the back. This institute grew out of a huge effort that Hopkins worked on building essentially the largest and the newest astronomy surveys and experiments. The Sloan Digital Sky Survey was essentially an experiment that changed the way astronomy is done and arguably science is done today. It is an experiment that essentially took more data in the first 3 days of its existence than ever before. So this is where, for me at least, big data starts. This is 2001, June, when the first data release goes public, and there's a long lead time essentially building all the tools. We were designing databases, building indexing mechanisms, and doing all the data management and preparation for handling the large amount of data that was coming down the pipe. And let me tell you, in 1997, 30 terabytes sounded like a lot of data. Okay? So this database currently is 36 terabytes. It's not a big database. It lives on a single server. And we are now building the next generation surveys. You might have heard of the Large Simplex Survey Telescope, or the LSST, a big 6-meter telescope in Chile, which is going to generate about 60 petabytes of images. And in astronomy, we expect to have about 100 petabytes of images in the next 10 years. So big data is really in our vein, and it's really in our focus. The tools we develop, however, often are very general purpose. And so in some sense, I'm a product of that development. I worked on these tools, and both on the mathematics side and the computational side. And these tools lend themselves very easily to other projects. And I always get this question, how is that possible? Urban planning or looking at vacant houses is completely different from what you see on the sky. And it's not quite the case, it turns out. But I'll get to this later. I won't dwell on big data, because we really just used to call this data. It's just called big data today. So I just want to say that if you were to show the whole of Sloan, which again is an old data set by today's standards, only covers a quarter of the sky once, then you would need essentially a screen that is about 500 football field size, right? So there's so much images and so much data that we don't get to see it anymore. We have to do mathematics and statistics to measure anything that we want from it. And the new survey, just to give you a scale that's coming up, is going to cover 3/4 of the sky every 3 nights for 10 years. So it has a 6.2 gigapixel camera. It will keep going on and on. So thanks to all this development and ideas that essentially grew out of these projects, we managed to secure seed funding for our vacant housing analysis. And that's how essentially the whole project took off. Before, it was more of a hobby project, more of a discussion. Let's see what one could do. And this was a very interesting proposal, only 2 pages, but it was written by 3 people, a mathematics person, a sociology person, and somebody from the city who happens to be a lawyer. So how is a collaboration like this can work? How these interdisciplinary projects really can take off? And this was one of those early examples where it really was working. And so what did we do? Okay, so this I wanted to have a little later, but we got very lucky, because soon after our project started, the 21st Century Cities Initiative was formed at Hopkins, which is a president's signature initiative. And as part of that, our project got a little more, not just visibility, but more support that we could build on. And this is our team, more of a core team, I should say. There is a whole pool of a stream of students who contributed significantly to this project. Phil, who we will meet very soon. Amitabh Basu is a faculty and a world-renowned expert in discrete optimization, who would have guessed that this is actually relevant for this project. Student Lenny, who is doing most of the hard work that we talk about. And on the city side, so the Department of Housing and Community Development, DHCD, is our close collaborator. In fact, the whole project started out with discussions, or by discussions with Michael Braverman, who is now the Commissioner of Housing, and John David Evans, who is the Director of Analytics. And also on our team is Ben Ziga, who is the 21st Century Cities Executive Director, and then Hannah Clemens, who is a research assistant. You will hear about their involvement in the project as we go down. And maybe this is a good time for me to take a short side note and say that this project is really happening because in the university setting, there is very many strong students who are really interested in the project and help out. So So the students who come and work for a summer or work for a semester and then maybe leave are contributing to this, and maybe they're not on this page, but there's many more people, probably about a dozen more, who have contributed, everything from high school students all the way to master's and PhD. All right, so it turns out there's actually a lot of data. Okay, so if you wanted to do some sort of analysis of this, go ahead. Everything is there, or most of these things are there. You can go to websites, the government websites, the data.baltimorecity.gov website, or other ones where you can get lots of information about almost every aspect of the city. Everything from parking fines to the vacancy information and so on. And there's more, of course, administrative data than just that will support and bring things together. And this data is actually being used, or it was even being used before we get involved in the project. Baltimore City Housing Department had an absolutely state-of-the-art technical solution and a team that was very appreciative of data and very knowledgeable about the data. So they really appreciated the value in data analysis and created maps that visualize every aspect of the city. So when they go about their life and make decisions every day running the city, they have this information available to them and look at these maps and make decisions accordingly. So what can we bring to the table? The proposition was that if we introduce another layer of abstraction or view or complexity using statistics, then we might be able to do inference and prediction that is useful and helpful for the city. Okay? And we weren't really just looking for a problem. Throughout these initial discussions, we actually established very well-defined problems we wanted to go after as a starting point. So if I wanted to give you sort of a 5-minute summary of what we are doing, is essentially the following. Data fusion, data science, bring together data from various sources, because while data is there, it actually is prohibitively complicated and expensive to do any type of new study. If you wanted to try out a new idea, you will not do that, most likely, because it just takes too much time to get ready for it. Us bringing together the relevant data sets into a unified schema and providing essentially tools, GIS tools and other tools to make the data fusion and the data screening and filtering possible made essentially our system the go-to solution. Now we can not only run our analysis on this system that is growing as we do our studies, but also we can very quickly try out ideas, and if we find that we're missing something, we can just ingest that and grow this database. So another side of this coin is social science, and that's another academic research that we are doing, and you will hear a little bit about it coming down the line later. It's about essentially modeling transition, understanding what's going on, and evaluating event policy. So we have spatial data, we have time domain data, and you'll hear more about it. And then there's this connection with Baltimore city government, where there are certain problems we can help with, assisting with strategic investment where appropriate, providing rapid response queries. So if there is an urgent question that our system can answer, then we are able to do that. And doing essentially inferences where we try to map out these unoccupied, as I mentioned before. So vacants we know about, unoccupied we have to learn. All right, so I'm coming from a very different background. In fact, this is what the internet thinks about the papers I write. So at least some time ago. So it's about galaxies and catalogs and surveys and cross-identification, which is this data fusion part. How do we combine, in a statistical, meaningful way, data coming from different sources? So that's where I'm coming from. I'm a data scientist and doing statistics, probabilistic analysis of things. So how do I go about then starting this project in the first place? Well, there's really two things you could do. You could go and talk to the people who have done it before and find out what they learned and what they do usually, or you could just let the data speak for itself. Do your own data science. And I decided to do both. Okay, why not? Have the complete picture. We started designing a system that will answer the city's questions, our questions, and it will be useful for research. Very much like we did it for astronomy and the Sloan Digital Sky Survey, whose pattern and template lives long, and now it's used in cancer research as well as on the domains. So there's two really basic directions you can start from. Start looking at low-level questions, the data-driven studies, that this is the stuff that you would be ashamed of not doing, right? These are the things that you would want to do just because the data is there. Understand what's going on, basic trends and analysis, descriptive statistics. So we'll cover that. And there is the very end of the spectrum on the other side, which is the high-level questions. Okay, so if there are these questions, then how do we address them, and how do we build a database that will, or a data solution that will answer them? So the 20 questions that you see here, and the gentleman on his sailboat is Jim Gray, who is a Turing Award winner computer scientist. He invented transactions. Every time you slide your credit card through a machine, transactions happen according to the rules and properties that he described originally to design the system. And he said he was absolutely phenomenal computer scientist who turned to astronomy for two reasons. Well, one was that he was really interested in it, but most importantly, he said that astronomy data is just absolutely unique because it's real data, it's big, and it's completely worthless. And what he meant by that was that nobody cares about any type of copyright or any type of privacy concerns. So you can actually work with that data, unlike any other data set in the real world, because that's usually protected by various organizations. So in astronomy, you can really try things out. So he worked with us, worked with the Sloan collaboration, and he said, the way you design a system is not by writing a 20-page requirements document, but you make the scientists or whoever is going to use the system, make them write down 20 questions. This is actually, seems like a simple thing, but it ends up being very, very deep in the sense that everybody will say, oh yeah, 20 questions, easy. Right? You start writing down the questions, then you realize after the third one that the fourth one is either the same one as you had before or similar, or you just maybe not seeing what else you could write. Point is, by making these mental exercises, figuring out what you really want to do with the data, you actually go through all the motion of figuring out what you need to build. And so what we started doing was essentially this, writing the 20 questions with Baltimore City, right? So essentially, instead of asking them to write a 20-page document what they want, we asked them, give us 20 questions. See if we can give you the answer for all that. So based on that, we actually built a database. We built this system that is a solution that has the usual components that you can imagine. It has GIS and it has time series analysis. And in the database, we incorporate a lot of analysis tools. And that's because that way you can very easily extend the analysis and try new ideas. Using the IDS infrastructure, the data scope machine that can crunch through data very fast, made it easy for us to create these systems, and we came up with novel indexing techniques to make the searches fast, statistics easy to do. So with this, we started mapping out vacancy. So this is a sort of very early on in trying to understand, like, how do you even work with this data? How does this look? And you could look at vacancy in 2010, 2015, comparisons across time. Or even better, you can start to look at how vacancy clusters. So we're just describing what's going on. And this is exactly what essentially in astronomy we do with galaxies. So, gravity is pulling things together. Galaxies are clustered, and that spatial clustering pattern is actually very interesting for us to understand the universe. The same tool, the correlation function that tells us the excess probability of finding a vacant house next to another vacant house, can be used essentially in quantitative studies. So we started measuring these functions and realized, well, we can actually go across time. So instead of measuring the probability of finding a vacant house next to a vacant house or a given distance away, you can actually measure the probability of finding a vacant house a year from now, a given distance away, or 2 years from now. So we could start to do predictions in a statistical manner, which then over time we can incorporate in our models. So we are really just exploring here the data, trying to understand what's going on, data-driven analysis. Another study we did, and turned out to be very interesting, and we are actually redoing this with new data and new analysis, is to try to understand neighborhoods that are so cardinal, so vital to the communities and also to the city. Are these neighborhoods are similar? Are they different from each other? How are they different? It's one thing to have your own culture or identity, but is there a quantitative way to compare them? So we started looking at their similarities in various ways, and building up essentially a graph, a similarity graph of all the neighborhoods that you can find. Why is this a good thing? It's a good thing because now we can try to find neighborhoods that are similar to each other, or neighborhoods that were similar across different epochs, across different times. And that enables now us to have some sort of control or comparison, because when policy makers make interventions, they tend to not think about statistical studies or control groups. This way we could introduce that and start to think about the impact of a policy or the impact of an intervention. Or we could even take it a step further and see if we can do some sort of unsupervised machine learning technique, clustering or grouping of houses, so that we can naturally come up with the neighborhood definitions. And very interesting things to explore in the maps. The collapsed vacants are essentially a study that we ended up participating in because of a tragedy. So what you see here is essentially abandoned properties on the left in Baltimore City, and on the right is houses that just collapsed over time. Yes, so there is I don't know exactly how many, not a huge number, but there is a non-zero. There's quite a few of these. The tragedy that prompted the analysis was essentially one of these vacant houses falling on a man who was listening to his radio in the car in front of that house. And it turns out that indeed these vacant houses can become dangerous, and at the beginning we were just racking our head on all sorts of theories of what could have happened to these houses. We were looking at old maps, looking at water, maybe there's underwater, changing things. We didn't really find any significant signal or trend there. However, it became very obvious quickly that the relevant thing to look at is whether the vacant house at the end of a row. And why is it important? If if the house is vacant and it's abandoned and it's not being used for a long time, the roofs cave in and the house disappears, and what happens really, the final result is just essentially of the facade standing there almost like a sail that the wind can then catch and take down. So if you were to now go and inspect these 17,000 vacant houses somehow, how would you start? Well, you could start with these ones, the ones that are at the very end of those rows. The problem is that it's actually not so easy. The algorithm is the following, right? You look for all the rows of houses, find their ends, and if they are vacant, you go and inspect them to make sure that none of those are dangerous to fall on anybody. The reason why this is hard is because even if you have the plans for the city where the rows of houses were built, that may not be accurate because over time, there could have been emergency demolitions that took care of or that brought down individual houses essentially in the middle of a row, which then created two rows. So now instead of having just two end units on the end of the long row, you would have 4 end units. And this actually happens, very often. There are alleys and so on and so on. So as simple as it might sound, the problem ends up being very hard. And the reason why we could solve this problem and work with the city to provide answers and find these was because we had the database with a proper GIS system, and we could start essentially writing down geometrical searches and geometrical equations that would then identify these houses. So in the wake of this analysis, there were, in 4 weeks, 400 houses. So there were 3,000 houses inspected right away, and 400 of those actually were demolished to make sure that no tragedy can ever happen again. And that was 3 years ago, and luckily, even though we had some big wins since then, there were no casualties since then. Vacant houses are a huge problem, as you can tell. This is a favorite of mine. So this little cartoon, even though you can't read it, and it's just a pencil drawing, is essentially what came out of a long meeting, which then was so long that we ended up moving to somebody's house, and on their kitchen table, we were essentially drafting and drawing up the next plan. Because what happens with this project is that you start out with a small scope, and as you start asking those 20 questions, they grow in scope. They become more and more adventurous and more ambitious. And we decided to go after a proper modeling technique where we can start to model and understand transitions in the neighborhoods and think about what happens with the houses. So these cartoons, some of them are just essentially capturing the kind of transitions we would want to model, but some of the information was there for me to understand what I didn't understand about the city. So remember, I'm a data scientist. I'm learning through this process. So I'm really, as you're learning about this project now, I was learning about the whole problem as we went. And one thing we identified very early on was that we needed more data. And that was something that was different from astronomy. So in astronomy, all that worthless data that Jim Gray loved so much is there for us to use, and we can write papers to our heart content. But in this field, in this arena, there's no free data set when you get to the edge of your currently available data. So we have been working really hard on identifying the right data sets and trying to figure out essentially what we can do with what we have and what is the next batch of data that we really have to have to make the next step. And this has been essentially an ongoing effort in parallel with the math and the research and the data science, trying to get more data into this. And so we are repeating and redoing our analysis over and over again. So the figures that you see might be old. We might have a newer version or a soon-to-be newer version as soon as we get the latest data. So so here is a project that I would like to spend a little more time on, because this is really at the heart of the problem, and shows how advanced mathematics can come to the help. So emergency demolitions is one thing, but when you actually have a little more budget and you can plan, you can do strategic investments in the city. And the question is then, how do you spend the money? So, okay, there's Governor Larry Hogan's Project CORE initiative. As part of that, $75 million were allocated for Baltimore. And the question is, what's the best way to spend this money? Okay, so it's not enough to get rid of all the vacant houses, and maybe that's not the best thing to do anyway. In fact, it turns out that about 35 million of this will go to demolition and about 40 million to rehabilitation and changing things in a different way. So what happened was, we were asked to provide feedback or input rather for the city's scheduling process, and as part of that, we were essentially identifying the lowest hanging fruits, right? So what is the cheapest possible targets you could go after if you wanted to have, many of the vacants demolished, and so on. This map, again, it has all the details of the GIS and the various features on our data set. This map was among the many when the city sat down and around the table decided about how the Project CORE budget should be spent, or at least for that year. And we were very fortunate to be flies on the wall. So sat in the back of the room and just pay attention how things are being decided and how what the process is, right? So as a math person, you would think there are algorithms and there are procedures and optimal solutions, and maybe there is. But the way this is done, of course, is as a committee looking at the maps, and around the table is everybody from the planning department and the housing department and historic preservation committee, and then essentially a part of the map and a part of the city is looked at, and essentially every house is really discussed in detail, in surroundings, the architecture, the street views, the aerial views, and so on. So, okay, fast forward a little bit. Our map was used there, and several times it proved to be valuable. But we were thinking, what if we could take this a step forward? Okay, what if we could introduce optimization to find the best configuration of plans, and this gets tricky because, of course, best is the hard thing to define, right? So you could think of maximizing the number of houses that you would like to demolish, if that's the goal, or maximizing the number of houses you would like to rehabilitate. But that's such simple objective function doesn't necessarily going to give you anything very interesting. However, maybe you could go after something more meaningful, something that somehow is proxy to the happiness of homeowners or the quality of life. It turns out that it's a very, very hard problem. In fact, you can prove it's so hard that you couldn't prove that you found the best possible solution. However, and that has to do with the fact that there's a budget. And the budget is a combination of multiple items. There are costs. Take just the demolition as an example, and this is just a toy example. We'll talk about how to extend this model beyond. But if you just think about there's cost associated with bringing down a house, But then if it's a row house, which is what every house in Baltimore is, or most of it in these markets, then you have to build support structures everywhere there the neighboring house is not demolished. So if you have a house that comes down in the middle of the row, you have to build two walls that supports the remaining houses. So there's a part of the budget that is linear and it's just a cost for every house, but there's the part of the budget that will be a combination of neighboring houses being demolished or not. And this actually is a problem that makes it very hard. It's a combinatorial optimization problem where essentially every house gets a variable, whether it gets demolished or not. And then you can go and optimize just for the maximum number of houses or something else. It's just a table of showing kind of the prices. So it's a non-trivial thing. The building a wall is expensive and almost as expensive as demolishing a house. So how do you find the best objective and how to solve this thing? What we decided to do is try to, this is again just a thought experiment, just a hypothesis. What if, and this is actually motivated by a personal experience, a colleague of mine who we shared an office, lived in a neighborhood that I consider a very good neighborhood, but he just didn't like it. He ended up ultimately moving away. But it took me 2 years to understand why he doesn't like his house and why he doesn't like his neighborhood. And that was because the one and only vacant house in that neighborhood was next to him. Okay? So there's clearly a happiness factor, and it's intuitive, but you can maybe quantify it a little better as well, which we did. There's a happiness factor or an unhappiness factor that corresponds to how far the closest vacant house is to your house. So one thing we tried was think about this as an impact, right? So try to measure everybody's happiness in the city given essentially the closest vacant house to them. And there's different ways of doing this, but the good news is that even though it looks like a very hard problem, it could be written in the form of integer linear programming, or ILP, that we can solve essentially in a reasonable amount of time. And what you see in these maps is essentially not the houses that we propose to demolish, but the impact that a certain plan would made to the city and the happiness of people where they live in Baltimore. So what you have in the two different pictures is with a budget of $5 million, trying to just maximize the number of houses will give you different spatial distribution than when you go after the impact. And what you see here is that here the solution is more clustered, more compact. It really is this very simple assumption about like what we think would be a reasonable proxy for happiness, already giving us things that seem to make sense, right? So I'm not saying this is a solution. I'm not saying this is the final answer. However, it's a step forward. It's a tool, just like providing a list of easy targets. One can build a tool that will provide different kinds of possible scenarios. And these scenarios can be tested in a numerical way with various models, and then can be vetted and decided on as we go about making the decision the same way as before. But there's a lot of guesswork that can be taken out. And one more thing that happens in these maps is here the different columns correspond to different budgets, same type of models, but for $5, $10, and $20 million, depending on how much you would be able to spend. So what is special, or what is really good about this global approach is that instead of looking at corner by corner different neighborhoods, we can actually optimize the entire city, right? And that will essentially seem to give us sort of priorities and modes, like what are the possible scenarios. And then, again, this is just input for decision makers. It's just a tool that we provide and could be useful when looked at during the process. But this is just the first step. So again, demo is just our prototype and test, which actually is a very useful one in the case of Baltimore, and it's very informative when decisions are made. But when you have an occupied house and turns into a vacant, that could turn into not just a vacant lot, but also a rehabbed house as well, right? And if you have a vacant lot, that could turn into other things, community gardens, urban farms, parks. There's a whole range of things that one can consider. And with every one of these transitions that one can propose for a given house or multiple houses within a neighborhood, there's cost associated with it. And we can formulate that in terms of a budget, and we can write it down. And then there is benefits. So again, it gets hard to quantify the benefits. One way to do it is actually think about the prices or the values of the houses. That could be a good proxy and there's other ways of course, measuring impact. We are collaborating with people who are experts in greening and urban spaces, also stormwater and food, urban food, to include all these things and solicit community feedback essentially to figure out what would be a good design scenario. So how does this work, or how will this work in real life? We have our data sets, we have measurements, we have constraints from that. We know certain areas had underground gas stations, so you can't have a park there, or if you do, then there's extra costs associated with it. We have all our data about the soil coming from Earth and Planetary Sciences collaborators. And so we don't know how much soil is required if you want to build a park. If you take down a large enough area, then you can turn it into a park. Yeah, the park in return will change the value of the houses surrounding it. And we can start writing down this as a model. We have the infrastructure to solve it. We come back with a solution, which then we can turn into a design pattern or some scenario working with landscaping people at MICA, which is the Maryland Institute for College of Art. And then go out to communities. So again, this is not something we want to do in the Ivy Tower. This is something that we would like to provide as a tool and then go out to the communities and find out if this is useful. So government, green spaces, and community developers. We have essentially a pending proposal to do this on a large scale, and the way we, again, envision this is that it incrementally gets better. So you start with what you have, you obtain some more data, revise the model, you write down that model, you solve the model, you come up with a landscaping plan and design plan, and then you solicit feedback, see if it works for everyone, and if it does, then great, but if it doesn't, most likely it won't, then you go back and revise your model, and you do a new plan and see if that works better. And so maybe it's science fiction. I don't think so. So I think there's a lot of things that you can quantify and a lot of things you can measure, and then you can start putting these together to come up with better plans, which again is not the answer or not the design, but it's a useful tool to guide the ideas around it and see if you can do something about it. And that's in the topic of combinatorial optimization. Who would have guessed that will be something that I work on, and I went down this path working with a collaborator because of this project. So while this is a very applied side of math, it also is driving essentially research directions at Hopkins. So it's a very interesting combination of how application and research happening in synergy. So After this, I wanted to talk about the predictive analytics part, which is concerned with what you can do if you actually consider time history and time domain data. But instead of me describing somebody's work or somebody who has been focusing on most of this, I figured it's actually much better to have him here and have him talk to you about the project and the work that he's been doing. His name is Philip Garboden. Phil Garboden, he's technically a PhD student at Hopkins, although he's defending his thesis in 2 weeks. And I've always considered him as a collaborator who is doing a PhD in sociology at the same time doing an applied master's program. So he was just essentially a great asset to this program from the beginning to act as a translator when I didn't speak the language, and he did. And also he is probably the most knowledgeable person I know when it comes to this intersection of these topics. So please welcome Phil Garboden, who will tell you about predictive analytics, and I will come back after him. I'm not going too far away, but yeah.
Say a few words? All right, great. Thank you. So what Tamás has talked to you so far has largely been about the problem of vacant, also known as abandoned properties in Baltimore City and what can be done about them, right? But regardless of how efficient your optimization strategy is for dealing with them, it's still very expensive to deal with abandoned properties once they become abandoned, once they've been boarded up, once they're no longer inhabitable, right? So what if we could develop a way to determine where, in which neighborhoods, there was about to be a spike in housing abandonment, looking at the way the neighborhood looks at the current moment? And fortunately, we have a great deal of longitudinal data. So this is just 3 neighborhoods in Baltimore. I don't know, for people familiar with the city, Franklin Square, Bel Air, Edison, and Oliver. And this is basically the last 10 years. I think it's a daily, I think I wasted time to do it at a daily level, a daily count of the number of vacant abandoned properties in those neighborhoods across time. And you can see that there's an enormous amount of fluctuation that occurs, and that this fluctuation is by no means consistent across the different cities. Different neighborhoods are behaving very differently. You have a neighborhood like Franklin Square, which is a high-poverty neighborhood in West Baltimore. You can see there's been a steady increase in the number of vacant abandoned buildings over time. But indeed, 10 years ago, there were already a lot. So we're going from 300 to 360. While this is a negative sign that Franklin Square is in no way improving over the last decade, it's going from a neighborhood that has already had an enormous vacancy trouble to one that still has an enormous vacancy trouble. There's plenty of optimistic stories, often caused by city interventions at some level, including nonprofit partners. The neighborhood of Oliver, which is just west of the Hopkins Medical School campus, has shown an enormous amount of investment from a variety of perspectives. And the number of abandoned properties has decreased from one of the city's highest at 750, and has decreased by over 750 abandoned properties, many through demolition, but also through rehabilitation and home ownership. What we care about in this next part of the project is identifying neighborhoods like this. So Bel Air Edison is traditionally African-American, working-class neighborhood. The houses are less likely to be row houses, more likely townhomes and single-family structures. And you can see in around 2006, 2007, there are only about 40 abandoned properties, which isn't ideal. Most neighborhoods have no abandoned properties in them. But that this has increased dramatically in the wake of the housing crash and the Great Recession. So now the neighborhood has, for the first time in its long history, a significant problem with property abandonment in 160. So what could we have done here to intervene? There are a number of options, all of which are cheaper than intervening here. And how could we have detected the fact that this neighborhood was about to experience this spike? Well, the biggest predictor of abandonment, not surprisingly, is unoccupancy, right? A lot of houses go through sort of a life cycle whereby they start with someone living in them. For a number of reasons, that person moves out. The house stays in relatively good condition. They're sort of turnkey. Someone could move in at any time. For a period, someone breaks a window, the rain gets in, animals get in, people sort of camp in them and so forth. And eventually it gets to a point where the city comes in, boards it up, and marks it as officially a vacant property. The problem is that there's no fine-grained, high-resolution way for the city to know if a property is occupied or not, right? The only public data comes from the Census Bureau in the form of the American Community Survey. This is at high levels of aggregation, both across time and space. You get 5-year rolling averages, which means it's in a time frame that isn't particularly useful for the city, and you can only get it at the census tract or block group level. And it's a probability sample anyway, so it doesn't cover the entirety of the city. So the question that we were trying to answer is, using data that's available to the city or for purchase, like the Postal Service data, is there a way to tell if the property is occupied? Ideally, you could identify neighborhoods that are showing disconcerting signs of unoccupancy, right? The healthiest neighborhoods in the world have unoccupancy. Houses get sold, renters move out, renters move in. In fact, if you have no unoccupancy, it's a sign of a overly tight neighborhood, like some places here in DC. But once you see a spike over what's called the natural level of occupancy, you know the neighborhood needs some form of intervention, or it's going to follow the path of eventual abandonment. The data we have at our disposal is water usage data. Fortunately, it's at a quarterly and monthly level, which is pretty good, but not ideal. We have Postal Service data, right? The Postal Service maintains a list of whether or not a property is occupied, in their view, whether or not they should deliver mail to it. And hopefully, at some point, we'll get data from the public utility here. So this chart here is these 9 panels are just the quarterly water usage measured in 100 cubic liter increments over the last, unfortunately, it's over the last 24 meter readings. So you get gaps when there wasn't a meter reading for a period of time. But this is roughly, you can think of it as the last sort of 5 to 10 years. And some of these are obvious, right? This one here, this property, has a pretty steady amount of water usage across time. Some sort of strange spikes and troughs that could have been vacations or some kind of plumbing issue. But in general, you can be relatively confident that this property is occupied. Similarly, the one right next to it, you can be pretty confident that this property is unoccupied. If you haven't used any water in the last 10 years, that's not an occupied house by any sort of traditional definition of occupancy. But then you have the sort of more, problem properties, not insofar as the property, but in the measures. This one here. So they're using below what any normal occupant would use in water. So do you think that is there a way to tell whether this is, say, a landlord coming in to water their plants or water their lawn or whatever, an absentee owner fixing it up, someone stealing water, a very low-level water leak, or an elderly person living alone who is just using an unusually low level of water? Similarly, you have strange things where a property will go from using no water to all of a sudden using a significant amount. And if you're in this quarter, is it realistically to assume that this property is occupied, or is there something you can see from the data that would let you know that this is a temporary aberration and it's going to go back? So the first step with this, right, is no matter what kind of proxy you're developing, you need to actually know for some set of properties what the truth is, right? You need ground truth data, right? If you train your models no matter how fancy the statistics you are on bad data, then you have badly trained models. So we needed to collect ground truth data. So this is where undergraduates come into this equation. This is Hannah Clemens. She did an internship with us. She spent a semester walking through 100 random properties in Baltimore and confirming their occupancy status spread out all over the city. And we felt a little uncomfortable about what it would mean to have her just knock on doors and say, hi, I'm just checking to see if anyone lives here, and then run away. So we actually made up a fake survey for her to administer, asking sort of like, if you know anything about survey design, like these are terrible questions about like, is the mayor doing enough for affordability? At least to give her an excuse to be there if someone answered. It's very easy to confirm a house is occupied. Someone answers the door, someone lives there, and so forth. It's very hard, of course, to confirm that a house is unoccupied, right? So we required that we had to knock on the door 7 times to confirm it occupied. 1 of those on Saturday, 1 of those on Sunday, and 2 in the evenings. Otherwise, you just think that every house with a working person in it is unoccupied. And as a double measure, before we marked it unoccupied, we checked with individual utility data, and we talked to neighbors to confirm that. So what we got was 100 properties, which is a lot in terms of the amount of labor that Hannah put in to get, not an enormous amount in terms of developing more sophisticated models. So it's sort of a pilot study we did of this. We got 100 properties that we were absolutely confident we knew at that particular point in time whether they were occupied or not. And we're thinking of sort of more like democratic sort of online surveys to see if we can collect more ground truth data so that we can train more complex models without risks of overfitting it. And we found first and foremost that neither the water data in and of itself, sort of the naive use of the water data, which is like, is it using any water or not, nor the Postal Service data was accurate, right? The Postal Service data, in fact, was pretty terrible, mostly because it takes about 3 months for a postal carrier to be confident to mark a property as vacant. So the lag is sufficient that except for the sort of long-term cases of unoccupancy, they're not going to show up in that data at all. But using a combination of the 2 models, we were able to correctly reflect the ground truth data on 95% of cases here. 90% of, so in the ground truth data, as we had hoped, when we picked randomly, we got something approximating the city's overall vacancy rate when you take out the abandoned, boarded up properties, which we know where they are, of 7%. And we were able to fairly well approximate the sort of diagonal of accuracy here, where our model correctly predicted the ground truth. We're still working on getting rid of these 2 and 3%, particularly this 2%, because the goal here is to really be able to identify the unoccupied properties. That's going to require using longitudinal water data, using longitudinal utility data, and ideally getting more fine-grained data on these, more fine-grained water data. Because if you think about it, if someone's using a consistent but very low amount of water every quarter, that can mean a lot of different things. If there's a consistent water data every hour, that's almost certainly a leak, right? Whereas if, except for the most impossible scenarios, if someone's living in a home, you're going to see spikes in water data at certain times of the year. It's going to follow predictable patterns. So once we get really fine-grained water data, which is available but is slow, we're going to be able to, we think, vastly improve in this model and get as close as you can humanly come to a real-time measure of housing occupancy that the city can use immediately to pick its intervention areas, and we can use in our sort of social science models of the city to talk about what is the process of abandonment and decline. Along the same lines, Tamás presented an objective function of happiness based on how close you live to an abandoned property, which is sort of the most straightforward and sort of obvious way to go about it. But the city cares also about the sort of overall value of the housing stock. If they're going to tear down some properties, it's going to cost them some money. Are they going to be able to get that back in terms of real estate taxes? And where should they be targeting their demolitions in terms of those real estate taxes? And in fact, this might be a very different answer than when you just look at total distance, right? If you have an area that has generally high property values, but an abandoned property, theoretically, at least that abandoned property is really an anchor, but not in the good way. Like it really pulls down the property values of all the ones around it, whereas one more abandoned property in a neighborhood that's already 15 to 20% abandoned might not be useful from this particular objective function. So in terms of what a good pattern is, it's all about what you're trying to optimize. Fortunately, here again, we have 30 years, actually, of actual sales records. This is for people who care about this type of thing, superior to what you get in your common data sources that only do realtor sales. We have the actual deed transfer data, so we're able to see everything from homeowner to homeowner sales, to realtors, to investor, to city condemnations, and so forth. And we can use that to look at properties that were sold in more than one time, right? You can't get a sense, and despite what you hear on the radio every month in terms of like housing indicators, you can't get a sense of how a market's doing by the average sales price of what's sold in the last quarter, because what's selling is never representative of a market. As someone who's trying to sell their home in the next 2 months, I'm acutely aware that Baltimore sales prices have gone up, but only because what most of is being sold is the nice stuff by the water, and my house itself has lost, well, hopefully, has maintained its value since we purchased it. Contact me if you need a house in Baltimore. And so we use repeat sales, and because we have so much long-term data, we're able to fairly robustly develop, using a log transformation, a trajectory of value detached from what it's actually selling in the city over time, right? And this is a pattern that's fairly familiar. The sort of the one here where the starting point is arbitrary. There was an enormous spike during the housing boom and pretty consistent decline thereafter. There's a little bit of a tail here, but there's so little data, at the very end of when you think about pairs, there's so little that overlap the very end. I'm somewhat dubious of this, and I think it's more of a consistent curve. More importantly, we can do this for the entire city, but we can do this for each census tract or neighborhood, right? And that allows us to extract a causal connection between property abandonment and sales price, right? Really, the hard causal problem, nut to crack here, is that, of course, abandoned properties hurt neighborhoods, and neighborhoods that are suffering have more abandoned properties. So how do you get the causal arrow, right? Well, you have to find something that is plausibly at least exogenous to the neighborhood's trajectory as a whole. So you control for the neighborhood's trajectory, and you look at small-scale micro-variation in the distance of a property, right? So as much as it's not at all random that I have a house where vacancies are increasing at a certain percentage of a year, it is plausibly random that I own a house that is 4 doors fronts away rather than 5 door fronts away from an abandoned property, right? That's sort of the random chances of this really small scale, which will allow us, and this is very much a work in progress, so unfortunately I don't have a punchline here, to get a vastly improve on the research literature in identifying the causal effect of abandoned properties on sales value, which then we can feed back into the optimization model and see what we get from that. This is a little interesting caveat along those lines. This is the change in sales price in Baltimore City of properties, again, over that 20-year span. The darker the blue here is where sales prices have gone down or stayed even in the purple, and the light is where they've gone up using repeat sales, other than that one little weirdness. What you're seeing is that they've gone down. This is where I live, right here near the block. They've gone down in the neighborhoods where things got most inflated during the bubble, right, which is the sort of quote-unquote Gold Coast of Baltimore by the water. Those properties have lost value on average over time, whereas the properties in some of the most distressed neighborhoods where the city's invested the most in in vacant property demolition and rehabilitation, the here and here and here, have gone up somewhat over time. Although obviously the color sort of scale on this is not optimized for contrast. All right, so I'm gonna hand it back to Tamás now, who will take it home.
I just put it back on. All right, thank you. So zooming back on the city, essentially the map that you just had before, we are looking into new techniques to actually work with satellite imaging and ask the question, can we use this information to predict unoccupancy? Can you use this information to learn something new about the neighborhood and the city? You could ask the question, can we find missing roofs? That would be a good indication nobody is living there, it's an abandoned house. Or the fact that we can find maybe a blue tarp on the roof, this indication, even though the house might be in bad shape, but there's somebody taking care of the house. So all these things one could start to think about, and just examples of these you can see. Another thing that we are gearing up for is a proper Bayesian probabilistic analysis of the entire city, where you build a hierarchical model and model every aspect of individual houses. At the same time, you model the population of the houses. And this is very much like what we do, when we do cosmological analysis of galaxies. At the heart of all this that we have talked about, and hopefully it came through, there's essentially applied mathematics and statistics, data mining, statistical modeling, machine learning, optimization, Bayesian inference, as well as data-intensive science, where everything from hardware development, software solutions, streaming algorithms. There was a discussion earlier about this today, how we can efficiently calculate things that otherwise are really hard to calculate, and maybe we don't have enough memory to keep everything to go. Database technologies, GIS tool indexing, is all part of this, and essentially you need a team that can handle all these tools at the same time. We have had success with this project, and it's been featured in the media, but what I wanted to say is that this really is just an early stage of the project. We are getting started. So we have a great core team that's able to do these technologies, and we have a strong stream of students who are doing really well. But we know the limitations, and we would like to go beyond what we can do right now, and actively reaching out to industries for collaborations. This would actually be strengthen the case for sustainable solutions. So academia clearly is not in the place of supplying a tool, which is what we would like to do for everyone and keep it running forever. We are, of course, as always, you're looking for support to make the next study that you haven't been able to do with the current resources. But maybe even more importantly, you look for data, because organizations will have the data that you don't have, and with that you can do a whole lot more. I think what's maybe special to an academic project is community feedback, which is something that we are really serious about, and we would like to think that this project is only a success if it lives beyond the research and it becomes part of the mainstream urban planning toolkit and people will use. So that's where I would like to stop, and thank you so much for the invitation. It's been a pleasure to come, and please contact us with questions, ideas, or suggestions. Thank you. Any questions?
All right, we have time for some questions. And there are some runners with microphones. There are 3 microphones or 2 microphones? I know I don't have my microphone on, and I can't get to the pot to turn up the volume. So we're going to have to live without the microphone, okay? All right, so we have a blue microphone. No, because you're going to need it to answer the question. Okay, we have a blue microphone, a red microphone, and what's the other color? Is there another color? Green. Okay, and when you get the microphone, I'll point to you, and you can stand up and tell us your name and ask a question. Tell us your name and whether you're a member, and then ask a question, okay? Got that? So we'll start with red in the back, and then we'll go to blue over here. And does somebody have the green one? Well, the green one will come to you. All right, red. You're on.
Thank you for very awesome. My name is Kyle O'Neill. I'm not a person. But I was curious, if you look at the secular trend in Western population, you see fairly healthy growth until about 1960, at which point a mysterious disaster strikes the city. I was curious to know if you have a theory of this mysterious disaster, and would that theory constrain the plausibility of various scenarios through climate change?
So this is something that's beyond what I can speak to as a data scientist, and I would refrain from speculating. Unless Phil would like to address the question, I would not offer a good answer, if that's okay.
Okay, we have this.
Would you like to?
Blue.
I have 2 questions. One, is it fair that my impression is that you're talking mostly about physical data of so they have bought sometimes very expensive mobile homes, sometimes their pickup, sometimes their car, and have gone nomadic.
You have to put the microphone to your mouth.
Speak to that.
All right, so let me see if I can answer the first part of the question. The data that we have is partly information about the houses, individual houses, and this is data that you can imagine, every real estate agent, would post when the house goes on sale. In addition to that, we have the history of the house, right, the time evolution, and that includes just public knowledge about the house, when it's being sold and things like that. And also some of the administrative data. So if the house becomes vacant, there's an official notice that gets published. So our data is essentially that, publicly available information. And what we'll do is synthesize from that a view of the city and its evolution. And we try to figure out what is a good strategy in this scenario so that you can make an impact on the quality of life. Now, it gets, I agree, very hard to quantify and understand what that actually means. Like, what's a good scenario? What's the best scenario? To optimize something, you have to be able to measure it. And what I can offer to that is that you can start with simple ideas like our proxy to home ownership happiness, and move on to maybe understanding the price and the change of values, in the presence of a park nearby versus a vacant house. But that's really all we have in hand to actually make decisions. And the real question is, to me, whether you can have a globally optimal solution to a city as opposed to doing local adjustments.
Red microphone. You get a pass. I don't know, is it?
I'm not sure.
You have to speak up.
Okay. This question is from Joel. He's joining us online. He's a member. And the question is, of the data sets taken, are there subsets of data that drive clustering? Also, have you applied this model to more than one urban setting, like with Chicago or other urban settings?
Very good. So it's a great question, and as with some of these analyses, interpretation is sometimes really hard. We don't have a huge statistical sample to draw from, and hence it's hard to generalize the results. And our analysis has been focused primarily on Baltimore, in fact, only on Baltimore. Now, the tools we develop are general purpose, and in fact, we intend them to be, and we work with 2 other cities going forward to make sure that this remains the same, that remains true, that our tools are general purpose. But our information, data, and our local expertise are local to Baltimore, and hence we are essentially, for now, restricting ourselves to Baltimore. But we hope to go beyond.
Blue microphone.
Thanks for the excellent talk. My name is Tom Ivey. I'm not a member, but I do work for the National Science Foundation. So you've said that you've offered these as tools to the community. My question is, when you go to the community, have you sometimes ended up changing your objective function of what you're trying to maximize or optimize as a result of community feedback? And if you have any specific examples, that would be nice to hear.
No, so this is great. So this is where we are heading, and in fact, what you're probing is a study that we haven't done. So what we have accomplished so far is the prototype and the simple case of studying demolition and understanding the objective functions that are hard, but we can deal with. And our next stage is to build the ambitious next steps to build that more general framework in which we'll be engaging with multiple communities. So as part of our NSF proposal, we have actually already teamed up with these communities, and these are connections that we'll be maintaining and drawing upon as part of the future project going forward. But I don't have a specific example because these interactions have not happened yet. The vision of creating this iterative procedure to make the tool better and better is yet to be implemented. What we have is the starting point, and we see how this will work, but we haven't done it yet.
The red microphone over here.
I'm Barry Vienna, and I'm not a member, but I love coming here. I realize this is an attempt to make a brand new use of your astronomical methods. Where in the development of your program or your programs in the future is there going to be an effort to decide if this is economically useful to the city, in this case of Baltimore, and that it really is helpful in the long run?
Thank you for the question. I maybe I didn't make this clear. So my background is in astronomy, and I think sometimes it muddles the water. But just because I have that background and knowledge of some of the tools, it doesn't mean that we are doing this because of that. So this is a new project independent of astronomy, but it happens to draw upon the expertise that we've developed and the data solutions we developed for astronomy. So this is a project that is on its own, and the economic aspect is certainly something that to be included. So as soon as we go to the limit where we start thinking about the prices and how prices are modulated by neighborhood changes and vicinity of park and other things, then economy will become a part of the equation and will become very important to us. But so far we are at the prototyping stage, where we are just gearing up for the real study, and we have established that we can deal with the data. We know what data we need. We have the mathematical tools to do the work, and now we just have to do it.
Just to make sure you understood your question, it's not charged to the city, right? So the economic cost is at zero, and we answer questions that they give us. So it's at least, worst case scenarios, we're hopefully doing them what they're asking. They seem quite happy with the collaboration, so it's a positive. That's what you meant by it.
Okay, maybe I didn't understand the question. So if you're asking if we are getting paid for this, the answer is no.
No, that's not my point.
Okay.
In the end, a very expensive process, I'm sure, needs to be economically useful. Because this costs a lot of money when the time comes when urban centers pay for it down the road.
Right, so we believe this will actually save money, significant amount of money, by doing actually optimization for that.
So we have blue at the back and then red. And then somebody will get the microphone to somebody else who has their hand up. But first blue, then red.
Hello, my name is Nathan Coleman, and I'm a member. So I really loved the idea of 20 questions to create the system as opposed to using a requirements document of some sort. Did you have any particularly interesting questions from the city or unexpected questions that they asked, or are they mostly pretty standard ones, like which houses are vacant?
So we are lucky enough to be involved with some of the creation of the questions. And as always it happens in any project we have been involved with, the first 3 and 4 are easy, and then it gets harder and harder. What happened in this particular case, and I think that's very interesting, is that as they were asking the questions, they were also rescoping the whole project, in the sense that they realized that we will be able to do these things. And then they said, okay, now let's step back one more step and ask more questions that are bigger questions and harder questions. So essentially, in the middle of the talk, I started talking about modeling the revitalization coming up with all these transition models. That was essentially what the larger question ended up leading to. So I would say we had the first sort of 5, 6 housekeeping questions. Then we had 3, 4, 5 that were the incrementally next thing. And then the following 5 were dream questions. And then we said, let's go after the dream, because it was within our grasp.
Thank you.
I think there's a red microphone back there. Could you please stand up?
Yes, I have a question.
What's your name?
Oh, my name is Osama Farag. I am interested in machine learning. I'm not a member.
Okay.
My question is, did you get questions like, giving the amount of resources, the money that they have, maybe they can invest it in either improving school district and then see if this will bring even much more money from private investors, if the trend of the decline start to change of the value of the property, or maybe providing like free childcare, things to increase demand for the houses, which basically brings the investors with private money. It's a different approach of achieving the same objective.
Okay, I'm not sure I followed the question exactly. Are you asking whether the strategies that one would like to develop has to do with the investor's interest? You mentioned school.
My question is, there is an assumption, or at least what I assume, that there is an assumption that investment in structure demolition or rehabilitation will achieve, but there is different indirect approach. So if I come and basically offer an excellent school district within the neighborhood, I will basically attract a huge number of demand for these houses and will help the house prices to go up. The investment then for the rehab and the demand for the lots and the property will increase. So ultimately it will increase happiness and increase occupation, increase the prices to go up with a different indirect approach.
So you're proposing that we should include in our model not just vacancy and parks and other amenities, but school would be, you think, the primary driver for some of these things?
The only reason is I thought for the school because it's probably the best approximation. Usually a school district is very good correlation for prices of houses. But there is also, for low income, if you provide free child care for multiple years, it might help, assuming they can get assistance for occupation.
No, it's a great idea to include that as part of the possible actions or part of the possible transitions that one could propose to do. So as you know, as there were those examples that we listed about creating parks or gardens, or you're right. One could think about landmarks and various things that one could put down in various places that would change the whole neighborhood's face. Possible. We would have to go and quantify it. So luckily we actually have data that allow us to do this, and we are in the analysis. So this summer we will have 2 new students joining us who will be looking exactly these kind of things. If you take one house that has certain physical properties, number of stories, number of bedrooms, and so on, you take that house and put it in different places in the city, so conditioning on its environment, what is its value. Then you can start to measure essentially this in a statistical way. And so, yes, school is definitely something that is worth looking at.
I have one question up here. I guess we can go Bob and then we go Terry. But, question.
Hi, I'm Stephanie Smiley. I am a member. And my question is for the speaker on predictive analytics. I'm just wondering, was it possible to use whether the property taxes have been paid for the year as one of your data points? would that have been useful, or?
Yeah, that's very much a useful thing. I think, and we consider incorporating the model. It's a really good thing. I think the issue with that is that there are lots of occupied properties that the property taxes haven't been paid for, and there are lots of properties that nobody's living in where the property taxes are being paid because someone's sort of, someone's waiting for the NARCI turnaround before they sell and things like that. So it's a very fuzzy signal as a measure, but we definitely should look at it because the more we can put into the model, really better. So.
Okay, Bob.
I'm Bob Hershey. I'm a member. Which of the things that you're measuring seems on the surface to be most correlated with the value of the property?
Well, so I don't think there are any surprises there. We haven't done a quantitative study of that because we are not there yet, and we are not using the price for quantification. However, I think there will be no surprises there in the sense that there will be the common drivers, which is how big the house is and where it is. What we are looking, or we will be looking very closely, is the subtle changes in the price that happens due to the environment. So somehow we would like to measure what happens if the same house is put in different neighborhoods. And so then you can quantify what would happen with the whole neighborhood if you, say, had a school or a park or something else happening in its vicinity.
Terry.
Bob Terry, a member. I'm just curious about what are your figures of merit as to how well the statistics is doing anything good or bad for you? I mean, I just didn't see any measures of success or failure.
Right. So in our optimization, the objective function has certain units, and what we are looking at very carefully is how that changes. So let me give you an example. If you were, say you are, let's the example of demolition. If you have a given budget, you can look for the optimal solution that is finding the best scenario for your objective, which we think is going to maximize the impact on the city. Or, all right, so the objective function, the way it's written, is essentially counting so you're measuring the distance to the closest vacant house for each occupied house and add it up for the entire city. So that's the objective function. Now you can do it different ways. You can have a certain distance, maybe a block or two, and count the number of vacants within that. Again, it varies with the variables, right? Because if you demolish a house, then immediately the number changes and so on. So the objective defines the unit. But what we look at then is how it changes with different scenarios. So if I look at the best solution versus I look for the naive solution, which would be just maximizing the number of houses, how much do I lose on the impact? And we can quantify that. So we can say, if you were to so first of all, there's many solutions that would get the maximum number of houses. Among those, which is the best one that will satisfy or optimize our objectives? And then how is that worse than the best objective? So we can then look at essentially how the impact decreases by artificially making the number of houses larger if that was the scenario or the goal for somebody. Like how would you actually lose on our defined scenario? Now the nice thing about the system we are building is, in fact, even without optimization, you can evaluate any scenario and compare it. So the figure of merit, this number that we add up, and it could be turned into a percentage or various ways of quantifying it to have it on a normal-looking scale. This can be evaluated for any design scenario. So if you come up with a plan for the city, we can plug that in and we see how well that does in our objective function. And we can have a whole suite of objective functions that we can then compare, and anyone can come up with a plan and we can try that. And then we can actually then go and optimize it and tell you what we think the optimal solution would be, and that could mean there could be a solution that doesn't actually implementable, but it might carry some qualities or some ideas that will influence the final design. So there are figures of merit, and that actually changes somewhat with the definition of the objective. But yeah.
Okay, we have. Is there a blue microphone there? So I'll take out blue and then red. You'll be the last question. So
Stuart Umpleby, I am a member. It seems to me like you're assuming that your variables have to be quantifiable cardinal numbers. In the social sciences, many times an event is adequate, like a piece of legislation is passed, or an employer closes down and moves away, and the workers no longer have jobs. And you were talking about occupancy. Did you look at whether the occupant was a renter or an owner? It seems to me that you're missing some very interesting information if you only concentrate on measurable variables.
What else would you concentrate on?
Interesting comment. So I completely agree that the numbers don't capture everything. Yet that's what we have. So unless there is some other way of including that information, I mean, it doesn't have to be a number, right? It could be categorical information. If there's categorical data, we can include that in our study. But if it is unknown to me, then I can't include it. So if you're talking about public opinions or things that one can somehow measure, even if it's a category, that's something we can include. So we can include it either in a form of an actual feedback from a community, or we can set up a web page where we can measure the temperature type of thing. So as soon as we can quantify it or put a label on it, then we can include it. If I don't know about it, I can't. Is that an answer to the question at all?
Yes. If you're writing a report on the history of Baltimore, you could have several chapters on the data that you're working with. You could also have a legal history. You could have an economic history. You could have a history of ethnic groups moving into the town. I wouldn't constrain myself to a certain kind of data. In the social sciences, many times what you want is a multifaceted description.
Right.
This is a discussion, not a question. So why don't we continue this during the social hour, and we'll move to the last question in the back with the red microphone.
Okay, my name is Saeed Musavi. I'm not a member, but my question, as a student of politics and data sciences, both of them, I was ready to listen more about the politics of your big data. And because it's very problematic if your model is a simple happiness, optimizing the whole city or optimizing the state value, I can see how the model, because if the city starts to listening to you, you become yourself, your model, your big data becomes a social force in itself. And you are going into a feedback loop that you make suggestion, and you are becoming part of the cause of the problem if you're creating problem or the cause of solution. So for me is that if I can simply see that your data can produce more inequality in the city, or where is the racial bias check on your model? Who is checking that? If a city starts listening to you, who is going to say, okay, you give me this data, but then again, this data should check your model. So how do you accommodate the politics of it? Thank you.
Right. So I don't. I'm not a politician, and I don't deal with the decision making or the political aspect of this. What we do is clearly, as data scientists, we clearly spell out the assumptions that go into our thinking. We formulate that, and then we solve it, and we think that the output of that will have some value. How that's used is based on essentially experience that people have with the city. And so one way as Phil pointed out, one way to use our data is to just ignore it, right? So if you think that you're not seeing anything that makes sense, then it means that our models are completely wrong and our solutions are wrong. So Phil is in sociology, and he has probably a better answer than I already have said. But what we see through these studies as we are going through, and again, this is an improving, an iterative study that gets more and more advanced, and we are seeing different patterns slightly. But what we see is that very simple assumptions that we make that are clearly independent of politics and racial issues and history. These very simple assumptions tend to lead to design patterns that actually seem to make sense, right? So essentially, by spelling out these assumptions and saying what we are trying to do, we provide something that is a different view of the same data that you already have. It's a different summary of the data, and that can be a useful tool in decision making or not. Okay. Again, I'm probably not answering the question because you're asking about the politics, and I will not answer that question because I don't know about it. What I'm saying is that we can build tools on simple assumptions that can get more complicated based on feedback and provide what mathematics and data science would tell you given the data about the city. And we hope that will actually be useful. How we know that it's going to be useful is it's just through these interactions, right? So essentially you discuss the results with communities, with government, and then you learn if there is anything valuable in the study that you're doing or not. So far, we have been encouraged to do this because the results seem to be meaningful. So that's all. And this is a process that we hope to engage in. Would you like to address this question?
No, whoa, wait. I think it's 5 after 10, and you can continue the discussion during the social hour. Let's thank Tamás for a wonderful talk, and also thank you to the graduate student. Before you go, Tamás, I'd like to present you with a token of thanks for coming here and spending the evening and giving a talk. Oh, wow. And that would be a signed and framed copy of the announcement of your talk. Thank you very much. Signed by all the members of the General Committee on behalf of the membership, and also a copy of Volume 1 of the Bulletin of the Philosophical Society of Washington, published a very long time ago, containing the minutes of the Society from March 1871 to June 1874, including the names of the founders and an explanation of why they chose to call it the Philosophical Society of Washington. And it wasn't to confuse everybody. Many people seem to think that we talk about Hegel and Kant and Aristotle and Plato, but we really don't. We're really about science, and that's why we're calling ourselves PSW Science these days. So thank you very much. So before we go, just a few housekeeping items before we adjourn to the social hour. If you'll bear with me, I get to make my fundraising request. So PSW depends on an enthusiastic, active, and capable membership. And without all of you, PSW would not be able to continue and would not grow. Sponsorships do not fully fund these lectures. Member dues are a vital contribution to PSW's financial stability and well-being. Without the financial support of member dues and additional contributions from members, PSW would not be able to offer these lectures for free to the public. So I urge everyone who enjoys these lectures to play your part in supporting PSW financially by joining the Society and, if possible, making an additional contribution. We are nearing the end of PSW's dues year, and dues are now at the half-year rate of only $37.50. So if you're not a member, please join now, which is pretty easy to do. Just go to our homepage, which shortly won't look like this, but for now, this is how it looks. Go to the membership button, pull up the application for membership form, fill it out, hit the submit form. You will then get the donate form, which asks you to pay your dues. You can pay with PayPal or a credit card. Please pay, and then we will review your membership application, and 99 times out of 100, you will be accepted to membership, and if not, in the unlikely event, we will give you a refund. So please join. Okay. As a new benefit for membership, in addition to receiving a copy of Volume 1 of the Bulletin, we are also making available a rosette. This is a lapel pin. It reflects the logo of PSW Science with the little bars on the side, reminiscent really of a coil, which is the symbol for induction, which was studied in depth by the great physicist Joseph Henry, who is the founder of PSW. And there's some other aspects to this, but if you are interested in, and you're a member in good standing, and you would like to have a rosette, would you please see Secretary Robin Taylor there, and Social Director, I think, was Social Media Director, Ann McQueen, up in the front here. She's going to raise her hand. Well, she's not going to raise her hand. So we're at the end of the season, and we have one more lecture. And it is the 87th Joseph Henry Lecture, and it is going to take place on June 15th. That's a different date than the one I've been telling you about, June 15th. And this year's Henry will feature lectures on the Cassini-Huygens mission to Saturn and the results they obtained. And the speakers, as we currently understand them, will be certainly Julie Webster from JPL, who will be giving us an overview of the mission history. She will tell us about the engineering of the craft, the instruments that it brought to Saturn, what they did, and the operations of the Cassini spacecraft and Huygens on its way to Saturn and once it got there. Phil Nicholson from Cornell, who we hope will be joining us, he's checking his calendar, will be speaking on the Saturnian Saturn system as a whole and on rings. Bonnie Barati, also from JPL, who has been with the Cassini mission since it began, which is 30 years, will be speaking on icy moons. Connor Nixon from NASA will be speaking on Enceladus. And hopefully Zibby Turtle from Hopkins APL will be speaking on Titan. We expect to have all this worked out this week, and we'll be posting the final program and additional information to the website in the near future. For now, thanks for joining us. The social hour ends at 10:30, after which PSW members and their guests meet at the Fairfax Hotel Lounge across the street. If you want to join us, please speak with Corresponding Secretary Robin Taylor, Membership Director Lloyd Mitchell, or me, sometime during the social hour. Please use the side entrance to exit. And I will now accept a motion for adjournment of the 2393rd meeting of the Society to the social hour. First, have a second. All members in favor? All members opposed? Meeting is adjourned to the social hour. Hey, Tamás.